Hello, my name is Dallas J. McKinney, and I'm a senior meteorology slash geographic information science major. And today I'll be presenting on my project um, on satellite and radar analysis of the June 21st, 2019 Super-Derecho severe storm. So let's get into it here. So first, what is a derecho? Although we know it's the Spanish translation is right, because it's a right-moving thunderstorm. The official definition is a widespread convectively induced straight line windstorm. That is produced by a mesoscale convective system, which has a large cloud shield, and also generates considerable damage from straight line winds, with damage being the primary element for classification. And then this damage path must be at least 650 kilometers long and 100 kilometers wide in one direction and the opposite direction. And this is according to the American Meteorological Society glossary. And then what is a super derecho? Well, this is an unusually strong derecho that's given this tag for emphasis. At least that's my definition. What is not a derecho is every line of clouds that moves through. So, for example, this line of clouds associated somewhat with the thunderstorm moved through the WKU campus in August 2018, but was not a derecho. It was really not even a severe storm. So, not every line of clouds is derecho. And this is what it looks like whenever you combine the satellite and radar together. You can see it has a large cloud shield uh, as part of the MCS or mesoscale convective system, but then also has the bow echo radar signature, as its derecho did uh, in 2019. And so we can see for the derecho in question, had a long damage path as I've plotted here with all the wind reports as squares and the tornadoes in triangles, hail in circles. They extended all the way from Nebraska to South Carolina over the course of about 24 hours. And why are we studying this derecho? Who cares? Because it caused 3 deaths, 4 injuries, it spawned 13 tornadoes, hundreds of winds reports, and then caused over 100,000 power outages. So great impact to both life and property. And so now we move on to the methods of how we'll conduct this analysis. And we use two. First is satellite. All our data comes from the GOES East satellite, which is a geostationary operational environmental satellite. And this is a form of remote sensing as the sun will send its energy and then some of it's bounced off the clouds and the satellite can receive it and transmit it back to the earth as data. And then also it can detect infrared energy directly emitted from the clouds also, so it even works at night. Our other method is radar, and we use the Weather Service Doppler radar, which sends out waves of uh, radio waves, and they hit the precipitation, some of it bounces back, and it receives it. And it does it at all these different angles so you can see into each part of the storm, see the precipitation inside. And it can pick up debris from a tornado, hail, and also, of course, rain. And this is a Doppler radar, and so it can sense the motion of the droplets and particles and debris and whatever else is in the cloud by the way it compresses or expands the waves. So, jumping right into the analysis, we know this is a severe storm as it caused really extreme wind gusts of over 65 miles an hour. And so, severe weather has these four ingredients: shear, wind shear, lift, instability, and moisture, which is SLIM for short. So first we'll look at shear. So right before the storm hit in Paducah, Kentucky, in western Kentucky, we can look at the radar and the radar velocity in this image, and we can see if I plot the winds here by looking at which way these little particles are being driven by the wind that the radar can pick up from bouncing off them, we see that the winds are opposite in direction near the radar, but then higher up in the air at these higher angles, or at 11,000 feet at most, is what it can detect at this time. It's coming from the directly opposite direction. So there's a change of winds and intensity of the winds with height. And so that's necessary to organize a storm as a necessary element for severe weather. The next part we have is lift, and this storm actually originated coming off the Rocky Mountains as a supercell, and it passed over Denver, hit an urban heat island effect, and became a supercell. The supercell continued moving into an unstable environment here, which we can see by plotting another parameter called equivalent potential temperature, which gives a measure of instability or how likely the area is to rise and produce storms. So we can see I've plotted out where the storm began here, 18Z or 18 Zulu time on the 20th, and how it tracked across the central and eastern United States. And it followed this gradient of instability uh, or potential temperature. And the last element is moisture, and we can look to our satellite imagery for that. You can see the dark green and lighter shaded values is extreme moisture ejected all the way up in the atmosphere. So we can see it start over here in Colorado and continue all the way to South Carolina. So lots of moisture coming in, mainly from the Gulf of Mexico and the Pacific. And so if we look at also the visible imagery from just light bounced off the sun into the satellite, we can see some of the vertical development or shadows cast by these clouds showing that they really went high up into the atmosphere. Um, so we know it's a lot warmer near the surface and colder up above. We know warm air likes to rise, try to cancel out that um, difference in temperature, and that's what really drove this storm. We can see how glaciated the clouds are, which is kind of this cotton, or not cotton candy, this kind of cauliflower look, and it shows it has lots of ice in these clouds. Another thing we can look at is infrared temperature, detected by the satellite, and we can see some very cold temperatures, which means these cloud tops are really getting up into the atmosphere. And we can see just how large this storm is. We see at one time it covers almost from Minnesota all the way to southern Missouri. So a really expansive storm. Um, and once it had the lift and the instability and the wind shear, it just drove itself all the way across the country, which is it was really long lasting and impactful. So what made the storm so intense? If we dig into radar, we can find that out. So the first thing to notice about the storm and why it's so intense over western Kentucky and southern Illinois and middle Tennessee was it had two radar bow echoes that merged. And so where these two merged, it was particularly strong. And we can see with the velocities, with the green coming towards the red away from the radar, um, that it had very extreme values. Some places detected winds over 80 knots or miles per hour. So if we look at this also, we can look at the different radar parameters, both the reflectivity, um, and we can look for why did it create this extreme hail in a county in western Kentucky called Ballard County. And if we look at the radar in a different way, we can see this hail core using looking at all these slices together in a radar software called GR2. You can see and that's the exact storm that produced this hail seen here. Another thing we can look at is a tornado it produced at land between the lakes. We see a cell here forming out in front of the main line of storms and producing a weak, what's called a radar couplet, where the winds are moving in opposite directions. So we see that, but then it disappears the next moment. And you can see it's a really brief tornado and highlights why this is so hard to predict. These brief tornadoes, they can still be very damaging, such as this one that destroyed a marina. So we get to the conclusion. Why was this derecho so strong? So you can think of it as a bunch of different factors adding up. So we had sufficient wind shear. This was the longest day of the year, so you had peak daytime heating for a long amount of time. And then this hit at the end of the day when there's a lot of daytime heating. Then also there were two bow echoes that merged together. And that helps to explain. So you can think of these waves, you can think of the longest day of the year is a really long wave, and then the daily diurnal cycle, and they all add up for this to be a really strong derecho in western Kentucky. You can see some examples of damage here um, across the area. Now I'll flash the reference slide and call it a day. Thank you for watching this video.